That's going to leave a mark.
Is that a pun?
Bunny fur, harvested from the backyard earlier this year.
Or your German Shepherd killed him.
Exactly. Whoa, whoa, whoa! Whoa! Settle down. So this is a weird thing. Okay, this is a weird thing. Balloons can exert non-contact forces on each other also. Get away from there. Like, are these two clearly?
It's going.
Don't do it.
It's going.
Don't do it. So balloons can exert non-contact forces on each other.
Yeah.
Weirdly, right? This is a piece of Teflon. I mean, it clearly exerts a large non-contact force on these bad boys. True? So we saw magnets can exert these weird non-contact forces, right? And then now we see that this, and you may or may not have seen this demonstration before. Can you just venture a guess as to what might be responsible for this?
Static electricity.
Sure. Do you think this has something to do with like static electricity or charged particles? What kind of charged particles do we have in our world that we're familiar with? Electrons and protons. And what are our rules? Like opposites attract and likes repel. Is that right? Opposites attract,
Yes.
likes repel. True for charged particles, not true for relationships. So I'm killing myself today, by the way. I mean, I'm just firing on all cylinders. This is a weird thing. This thing's called a fun fly stick. It exerts a large non-contact force, but what do you think might be true about the charge of the Teflon versus the charge of the fun fly stick? Does it make sense they might be opposites? Yeah, totally, right? Boom. Oh, see now they're very sad. Anyway, so that's enough of that. But what's the point, right? So flashback to 2.5 minutes ago. Remember, I pushed the two carts together with the spring, and they moved apart. Where was the energy stored? In the spring, and then we saw it manifest in the motion of the carts. True. Then I did it with the magnet carts. Where did you guys decide that where the energy was stored? I mean, you guys said magnetic field. We'll see how that, Okay. Do we see a non-contact force here? We do, right? What I'm going to do is I'm going to push them together. I'm going to let them go. And what did you notice happened? Did they move away from each other again? They do, right? So what we're seeing here is obviously, right now, there's got to be energy stored somewhere, because when I let them go, do they move apart? Do we see the energy manifest in the motion of the balloons? So where do you think the energy was stored before I released the balloons? Check your neighbors now.
Talking about electric storage.
Yeah, but are they actually being changed at all or deformed at all? I feel like it's...
Well, I kind of look like different magnets were stronger than others, so maybe it's like this. How different they act with each other, that's how it can be stored.
But I feel like even if there's, even if you change the magnitude of how many there are, you're still not actually changing it or forming.
So you can't be more positive or less positive.
Well, Oh, I see what you're saying. So you're saying like the imbalance itself is the deformation?
More imbalance,
Gotcha.
stronger the reaction.
Then water.
So like,
That seems
he had a
weird.
stronger magnet and that seemed to pull it more than when he,
Okay,
you know, or pushed more.
what do you
The only
think?
thing I keep having in my brain is like those pictures of like where it shows like a magnet.
Totally looks
And,
like that, doesn't
it looks like a little lines.
But there's stronger magnets and weaker magnets, right?
So, the thing about this though, and magnet might be a possibility, right? Magnets might be a possibility, but if I bring this magnet close to this one,
It attracted it.
it totally did. Now, what should happen then if I turn this magnet around? So there's something else that's going on here. These balloons they're rubber, they're not magnetic. Okay? You with me on that? I mean, clearly the magnet can't be like this magnetic force. All right? What might be... Where might the energy be stored in this? Like, I've been training on Dagobah. I don't know. Where might the energy be stored? You're allowed to venture a guess here, right? That's consistent with some things we may have seen earlier today. See, my point is that there's two kinds of forces in this world, okay? There are contact forces, and there are non-contact forces. So what can provide a non-contact force? Right, we just saw that earlier, right? So magnetism, we'll call it magnetism, we use the ism form.
Or like electricity.
Sure, right? So magnetism, so electrostatics, right? What do you need to be, what do you need to be in order to exert a magnetic force? A magnet, right? What do you need to be in order to exert some sort of electrostatic force or static electricity force? Some sort of charged particle, right? Like a proton or electron. Is that cool? Right? Is there another kind of non-contact force we've seen before? Totally, right? Like if I throw this up in the air, it's coming down. Like something's got to be pulling it down, true? Right? Without touching it. Right? So these are our three non-contact forces. What about the contact forces? Right? We don't really need to like label them, like go through them because it's everything else. Right? And yes, air is a contact force. Okay? Air is a contact force. You know how you know if you're a contact force? If you can buy it at the store or I can hit you with it, that is a contact force. Okay?
You can buy magnets at the store.
You can. I can also hit you with them. So, here's a little science, right? Science content warning. Okay? Science content warning. These non-contact forces are super spooky. So what scientists did is to try to kind of like alleviate the spookiness of these forces. They gave them a name and a conceptual framework. These are actually not really called non-contact forces. They are called field forces. Okay? They are called field forces. And the field, just in general, a field is an area around one of these non-contact force conveyors. So around the magnets or around the charged particles that has two jobs. Okay? It has two jobs. Hold on. I know what the two jobs are. So the first job is to provide a mechanism so it's provide a mechanism for the non-contact force. So instead of saying, oh, it's just a spooky non-contact force, we're like, nope, the field is supplying the force. Right? Not that that's any better. It's still spooky because I can't see a field, but I look at these two and they should be resting against each other, but they're not. Right? There's clearly some sort of force, and we say, oh, it's the electric field that's providing the force that allows you to repel each other. Is that cool? And guess what the second thing is? Okay? The second job of the field is to store energy. That's why we like the field concept, is because it allows us to say, oh, where's the energy stored? When I push those two carts together, where is the energy stored? Oh, it's stored in the magnetic field, and then it's transferred out to the motion of the carts. I push these two bad boys together, where's the energy stored? Oh, it's stored in the electric field, and then it gets transferred out to the motion of the balloons. Ready? I have my dropper popper. No, I have my table popper. It's a great save. We'll let it go. It's going to go up and it's going to come back down. We knew it was stored there in the popper. Then we saw it manifest in the motion, and when it got to the top, we didn't know where the energy went. Where was the energy stored? Check your neighbor now. Where's it stored? Oh, that's so exciting!
So can gravity hold on to energy as long as like magnetism, electric?
Well, like if you,
It seems like one of them could hold, like gravity just immediately releases it once it gets.
well,
or-
but like if it, I mean the tissue box, technically like you push it off,
So,
it's stored.
where's the energy stored?
But it's sitting on top of a table.
Gravitational field.
Where's the energy stored? Nice and loud.
Gravitational
In the
field.
gravitational field. So this is the way that we're going to conceptualize our energy. Okay? Is that energy can be stored in springs and rubber bands. It can manifest in the movement of things. And that could be like bulk movement of big objects. We're going to see later on. It could be manifest in the small movement of particles. Okay? And it can be stored in fields. It's like a huge revelation. Right? The fact that there's energy stored in fields, because it gives us a way to talk about these things without having to like pretend or like do something like that. Does that make some sense? I'm going to mention one more thing and then we're going to break, because you guys have been holding on really tight and I appreciate it. Okay? If I take this cart watch me, I'm going to tip up this end. Oh, there's going. There we go. Good work, Don. Okay. If I take this cart and I send it up this ramp, and it comes down. When it got to the top of the ramp, where was the energy stored? It's in the gravitational field energy, right? So we say it's stored in the gravitational field, which, and we'll talk more about it, it's really an interaction between the cart and the earth as a whole. But the thing is, like, so, like, up until now, and then this manifests in so many different textbooks, you would say, oh, well, at the top, it's potential energy, and at the bottom, it's kinetic energy. You guys ever heard this? Yeah. Okay. We as a group can do better than that. And let me tell you why. This is what I was talking about earlier, about how we try to reconcile our everyday language with our science language. Because, you know, when I was young, they used to say, like, you know what, Don, you got a lot of potential. Okay? But what does that mean? It means you're not good now, but you may be good in the future. Right? But the problem is that when I say that in terms of, oh, it's potential energy, what you're actually telling me is it's not actually any energy. It could be energy sometime later. But I would totally disagree, because when it gets up there, there's a ton of energy stored in the gravitational field already. and then it gets transferred from gravitational potential, or from gravitational field energy to kinetic energy as it rolls down. But just saying it's potential, I think it leads kids to be confused with their everyday concept of that versus our science concept of that. And I think that's a little, don't do it. Oh. All right, so let's take a 10-minute, okay? Let's take a 10-minute brain break, and we'll go from there.